So in this video, we're going to think about relations. We're going to define what a relation is. We're also going to give the definition of a linear order, what we'll call a strict linear order, and also a well ordering, and we'll give some examples of these kinds of things. And remember from the last video, what we proved was that if we had a set or a few sets, we could prove that the Cartesian product of those sets exists. And this is exactly what we would need in order to give the definition formally of a relation. Definition: a binary relation on a set A is a subset of A times A, where this is the Cartesian product of A with itself. And just as a remark, so we're going to be thinking a lot about orderings on sets, and these are certain kinds of relations, and we would normally denote these with less than signs or curly less than signs. So if the curly less than is a relation on A, well, we would write this. So just as an abbreviation, we would write something like this. We would write A comma curly less than. So that's just a way to abbreviate this less than sign being a relation on A. And further, just for some notation, we write X is curly less than Y instead of the ordered pair XY is an element of curly less than. So if we're being really, really formal, what we have to write if we want to say that something is less than another thing is we'd have to say that that ordered pair is an element of curly less than, right? Curly less than is a set of ordered pairs, but that notation is kind of gross. So we'll write this X is less than Y, and this is and I hope everyone will forgive me. Okay, so that's the definition of a relation. So what we care about ordering, so we care about certain types of relations. So let's give the definitions of some properties on relations that we might care about. Let's erase this. So the first type of thing that we're going to think about is, fix a set A, fix a set A, and a relation, on A. Well, we have the following definitions. So we'd say that this relation is transitive well if the following happens. So if and only if what is true. So if and only if for each x, y, for each x, y, and z in our set A, well, if x is less than y and y is less than z, then x is less than z. So maybe I want to write this here. So if x is less than y and y is less than z, then x is less than z. So if something were to be a relation or an ordering, if we were to order sets in some way, well, this would be something that we'd expect out of orderings. If something is less than something else and that thing's less than something, well, then the first thing had to be less than the last thing. What's another property that relations might satisfy? This relation is called irreflexive. Irreflexive. If and only if what is true? Well, if and only if every element is not less than itself. So if and only if for each x and a, it's not true that x is less than itself. And well, one way that we might write this, so again, as an abbreviation, one way to write this is we might write x is not is not less than itself. So that might be something we might write something like that. But that's what it means to be irreflexive. And the last definition for now is that if we'd say that this relation is total if and only if what happens? Well, if and only if you take any two elements, one is either less than the other or they're equal to each other. So there's three options. So if and only if what happens? If and only if for each x and y in A, there's three options. Either x is less than y, or y is less than x, or they're equal to each other. So that's what it means. That's what I mean when we say that a relation is total. Oh, I guess I had one more thing. So a relation is a strict linear order. Relation is a strict linear order. Is a strict linear order. Well, if and only if what? If and only if the previous three propositions hold for that relation. So if and only if 1, 2, and 3 hold. 1, 2, and 3 hold. And so again, where does this come from? We're trying to generalize something maybe like the ordering on the real numbers or the natural numbers or something like that. Every number, this 1, 2, and 3 all hold for the rationals or the natural numbers or anything like that. So this, though, the way that we've been kind of doing this definition of an ordering, we're calling it a strict linear ordering on purpose, right? And it's because we don't want that. If we're using this strict linear ordering to kind of mention that we don't want something to be strictly less than itself. But what we can do is that if we have a strict linear order, we can kind of define kind of a non-strict linear order. So how do we do this? Erase this. So what's another definition? Well, if we're given a strict, so if a comma curly less than is a strict linear order, oops, we already defined that. If a comma less than is a strict linear order, then we can define it'll be curly less than with another line under it to kind of represent less than or equals to. So this is going to be a relation on A by saying what? Well, x is going to be curly less than or equal to y. Well, if and only if what happens? If and only if either x is strictly less than y or x is equal to y. And if we have a situation like this, we'll just call this we'll call this thing a linear order. So call a linear order. Now, to be honest, I might call the strict less than a linear order. It's going to be implied from the context whether or not we mean a strict linear order or a non-strict linear order, just by whether or not we have the less than sign with the line under it or not. I think I have one more definition, and then we'll give a few examples. One more definition. Well, let's say that we have a strict linear order of a comma less than is a strict linear order. And well, what else do we have? Let's say that we have a subset S of A, and some element of our set S. So we have a strict linear order, a subset of A, and an element of our set S. So X is called a, X is, we're going to say that it's the least element of S. And so I guess technically it's the least element of S with respect to our strict linear order. So this is the definition. Well, when is this going to be true? Well, if and only if it's less than all of the other elements of S. So if and only if for each y in S. So we could write this in two ways. We can either write the way that I'm about to write it now is that X is less than or equal to all the elements of Y, or we could say, well, for every element of S not equal to X, X is strictly less than Y. So an element is the least element of a set if it's less than all of its other elements. All right, so what are some examples? What are some examples? So let's say that our set A was omega. And remember, omega is kind of the set theoretic natural numbers. So that's going to be the set 0, 1, 2, and so on, where what were these numbers? Remember we defined 0 as the empty set and 1 as the set containing 0 and 2 as the set 0, 1, and kind of generally the set n as the set of all natural numbers before it. So let's say that we had this set here. This is our set omega. Well, we can define a linear order on omega in the following way. So we can define we'll say that let's say that m is, well, less than n if and only if m is an element of n. And this actually corresponds to exactly what the usual ordering is on the natural numbers. What we think about being kind of less than, two natural numbers are less than, if one natural number is less than the other one, what do we mean by that? Well, in this context, it's exactly this ordering here. And if we're being really, really, really formal, what we'd have to say is that, so formally, we're not really going to do this, but it's good to be. We're not going to be as formal about it all the time, but it's good practice. Formally, this set less than, well, this is going to be equal to, right? It has to be a set of ordered pairs. It's going to be equal to all of the ordered pairs m n in omega times omega, such that what happens? Such that m is an element of n. Right? If we're being really, really formal, that's what we mean by our ordering. Okay, so let's kind of continue on with this example. Let's say that S was the set of all elements of the natural numbers. So it's all natural numbers that aren't equal to the empty set. Well, then what is the least element of this set? Well, the least element of the set is actually going to be 1. So then 1, that's an element of S, is the least element of the set. So just to kind of comment on this a little bit further, the empty set is 0, right? So this is all natural numbers that aren't 0. So this is really just the set 1, 2, 3, and so on. And if we wanted to be really, really formal, what we'd say is that, well, the least element of the set is really the set containing the empty set, because that's what our definition of 1. That's what our definition of 1 was. So maybe if we're being kind of using the notation before, it's the curly less than least element of the set. So I have one more kind of crucial definition for us, that of a well ordering. We'll give some examples and then call it a day. So definition. So definition is we have a strict linear order. So is a well ordering. And sometimes I might write WO as an abbreviation. Well, if and only if what's true? If and only if, well, it's a linear order. It's a strict linear order. And what else has to be true? Well, every non-empty subset of A has to have a least element. And every non-empty subset, let's call it X, has a curly less than least element. So this is going to be an incredibly important type of linear order for us, well orderings. Let's give some examples of this. The example that I think everyone is familiar with is that the natural numbers with the usual ordering is a well ordering. So is a well ordering, right? Because every single non-empty subset of natural numbers has the least element. Well, let's consider a slightly different set. Let's consider the set A. Let's make this all of the. So we haven't technically defined what the rational numbers are, but let's pretend we could do it. So let the set A be all of the rational numbers that are bigger than or equal to 0. Well, this, and it's this set here. We have to kind of tell, we need to say what the ordering is. So let's just say it's with the usual ordering. So with the usual ordering. Well, A has a least element. This is not going to be a well ordering. So this is a non-example. So this is a non-example. The non-example. A does have a least element though. So A has a least element. Namely 0. Everything is bigger than or equal to 0. So it has a least element, but it's not a well ordering. Why is it not a well ordering? Well, we would need to give an example of a subset of this that doesn't have a least element. And so rigorously, this set here all things that are strictly bigger than 0. This is a subset of A, but it doesn't have a least element. So it doesn't have a least element. And then what's one more example? A little bit kind of foreshadowing what we'll be talking about in a little bit. One more example. This thing is sometimes called omega times 2. But so what's 1/3 example? Is that if, let's say that we took a bunch of dots, and I'm going to do dot, dot, dot. So this might be like 0, 1, 2, and then dot, dot, dot. And then let's have another set of dots that occur at the end of this. So we have another set of dots, and they go on forever like this. So this set of dots here there's omega many. This is kind of like a copy of omega. So we're kind of listing out all the natural numbers. And what we're doing here is we're listing out another copy of the natural numbers, where the second copy of the natural numbers is defined to be bigger than all of the first copy of the natural numbers. So this thing you can show is actually also a linear order, or is also a well order. So this is a well order. And we'll actually be denoting this later. This is the ordinal omega plus omega, or sometimes this is written omega times 2. And the ordering of this, unfortunately, is important. But yeah, so I'll stop the video there. Going forward, we'll talk some more about strict linear orderings and well orderings, and work towards a definition of what an ordinal is.